info. We'll give you a sec. You can check. It's okay. We're not rushed.
Yeah.
So for all the students who are in here, while we wait, and we're just going to get started as soon as we. Excellent. We get over all these things. I mean, we're here from Matrox today, specifically from the imaging division. We point out that we do have mentors available this evening in the Matrox lobby in case you have questions related to the challenge. So please feel free to drop by and ask questions. We know for some of the challenges you need to set up and install some things. So we have people around to give you a hand with that so you can kind of get bootstrapped this evening and get started. Of course, people will be available tomorrow. But, you know, my poor director is sitting there by himself, and I'm sure he'd love some company. So after this, feel free to go there if you have specific questions about the challenge and all that. Yeah. Yep. There we go. Can you see the full presentation now? You should be able to only see the presentation, right?
Wait, Catherine, you're the viewer. You need to change your view.
Right. Okay, no worries. So tonight, what we're going to be talking about is computer vision and machine learning in industry. So it will be sort of tangentially related to the challenges. The idea is to talk a bit about like what we do and what our industry experience has been, and kind of how, you know, machine vision and machine learning have kind of come together in the industry space. So that's kind of what we're going to talk about. So let's see if we can get the slides. So who are we? Well, we're from Matrox Imaging. My name's Dirk Dubois. I have a master's in engineering from the University of McGill. I also did my bachelor's there. And ooh, our transitions are backwards. There we go. Okay. And there's this great old photo of me from my bachelor's. So what I do is I design software for machine vision. So I'm principally a developer who works on graphical user interfaces for our vision systems. And then my co-presenter, Benham, is here with us, and he develops machine vision solutions. I'll let you say hello.
So I'm Benham, and I develop machine vision solutions. I work in a group called Vision Squad. So once there is a company asking for solutions, we use our tools to develop a solution for that specific problem that the company has, for example.
Yeah. All right, so, well, what is Matrox? Well, Matrox has two major divisions. We've got the video group, which I know less about. They have their own workshop, and they do things like display walls, broadcast and media streaming. So everything that you need to do when you're trying to do something like this, you want to record this session and put it live to YouTube. Well, we make products and services to help you do that. And that's what the video division does. But we're from imaging, so let's talk about imaging. So in the imaging division, we do everything that's hardware and software for machine vision. So you have, you know, some sort of analysis you want to do of images. We provide the hardware and software to make that possible. And we've been around for about 40 years. So believe it or not, we're a Montreal-based company. Lauren Trottier is the founder of Matrox, along with Branko Matic. And, you know, we're Montreal-based. All the engineering work and development and design gets done here. And most of the manufacturing gets done in Montreal, too. We have our own assembly line. And we manufacture a lot of our hardware right here in Montreal. So what is machine vision? You know, just to kind of give you a bit of background. Well, machine vision helps automate inspection. So we want to do things like detect objects in images. We want to measure something in an image. You know, so detection is great. You know, you can find a piece. But once you found a piece, often, like, if you want a robot to be able to come in and do something, you have to, like, measure it. You have to know something about it. And so, you know, how do we do that? Well, we provide this tool called MIL, the Matrox Imaging Library. It's a big API for machine vision. So it's basically a software development kit that customers develop with, and they use it to code solutions for machine vision problems. And that's kind of what we develop. And we've been doing that for a very long time. MIL's been around since 1991, so for a very long time. So who are our customers, and like, what do they want? Well, they have really tough demands. So our customers really are looking for long-term compatibility, software that will be around and be stable and fulfill their needs for a long time, because they have these big projects, right? They're going to be around for many, many years. So they need a lot of long-term compatibility. They need really accurate results, right? Because they have like a factory floor somewhere where they're looking for parts. They're trying to pick up stuff. And, you know, everything that's missed is, you know, lost revenue, lost money. And they have real-time constraints. You have robots in the mix that have to pick and place parts. You have some sort of biomedical scan. You know, you have things that have to happen within a certain time delay. So they have real-time constraints. Whoop, I feel like I missed a slide. Nope, there we go. Okay, cool. And I will play this great video and hand it over to Bam. Go ahead.
Yeah. So some examples of what they explained to you. Here you see a robot that is scanning the circuits and it's doing the wire bonding. So it's there is a camera looking at the circuits and it decides where to start the wiring and where to end the wiring. So how it's using our tool, we have a tool called pattern matching, and in that you define a pattern. For example, what you see on the right side, the rectangular shape, and then once you capture an image from the circuit, it goes and it searches in the new image and locates that pattern. And by knowing the location of that pattern, they can decide where to exactly start the wiring, and it gives you the sub-pixel accuracy here. So it's pretty accurate. The other example would be deep learning module that we have. For example, in food industry, you can use deep learning to decide if you are producing a good product or not. What you see here, it's images of the muscles captured by X-ray cameras. So what do I mean by a good muscle and a bad muscle? The bad muscle would be a muscle that has shells on top of it. The ones on the bottom that you have the red rectangle around that, they are the bad muscles because they have the dark spot on top, which are actually the shells. To perform that, we first, as I mentioned, we captured the images. Then we use our blob analysis tool because our background is white and then the objects are black. So we easily can just distinguish the objects and locate them. And then once we have located the objects, we crop them and we train a deep learning neural network to be able to learn the, good and bad muscles and then predict them during the production. So we gained 98.6% accuracy after training the model, and our network actually works on CPU, and the prediction speed per muscle was about 1 millisecond per muscle or per boxes that you see.
Give it a second, loads.
Yeah, exactly. Yeah. So here we're gonna show you how to train actually one context to be able to learn and then predict if muscle is good or bad. We have a lot of images of the muscles labeled, so you see the green and red boxes under the images, so it says if it's a good or bad image. We have done also augmentation, so that's why you see some images are darker, some brighter, and there is rotation, there is noises added, smoothing a little bit, different type of operations to make the trained context more robust. And you see like this one has the darkest spot, so it's a bad one. After we have the data set, we need to go and train our context. We give you our parameters to training, like you have the learning rate and all of these. Here I'm changing the batch size because my GPU can handle it. Then you choose your context, your train set, and your dev set, and you just let it run easily. Once you start the training, you will see two different plots there. One on the left side and one on the right side. If you're familiar with deep learning, you know that there is the loss value, which is our optimization error. That's what you see on the right side. And what we want to do is actually train our network to learn how to minimize this error. And what you see on the left side is the live feedback from the context to know if the trained data set and the dev set are giving us good results. So it's actually the error of our train set and the dev set. We are choosing the best trained context during the epochs that we are doing. So you don't need to worry about problems like overfitting and this kind of problems that happens during the training. And you can see that here, for example, the current epoch is 15, but we get our best, which is 13 so far. And it goes on by the time. Since we are looking for accuracy of 90 to 100 or 95 to 100, it's better to switch to the logarithmic scale. So we have a better visualization and more accurate visualization to understand how close we are to the goal that we want to go. As you know, it takes time a bit to train, so we skip this part and we go to the place that it's ready to use. Yeah,
there we go. Sorry about that.
No problem. So once the context is ready, we see that the slope is nice. It's starting high and it's going down. Then we have our test set. We want to test if the terrain context is good enough to deploy. Then we predict on the test set using the train context, and we have some analysis to do to see if it's a good one or bad one. So the tools that we provide, there are some charts that you see the ratio. There is confusion metrics that you can see if it's good for each class, how it's behaving for each class. And then there is the chart that you can see the distribution of the scores, like how many images are predicted with a score of 100%, how many with 90 to 50, or for other classes, how it was. You can just have it like quick visualization of the behavior. So we can use also deep learning for other problems. For example, pastas, once we are looking at them, they don't have a specific pattern. Every time they're mixing, they have a new pattern we are looking at. So deep learning is a good tool to classify different type of pastas. For example, here we have the images of the pasta, and we can say which type of pasta we are looking at. The other example would be OCR. We have a product that we want to read a string on top of it. We grab images. Here we are performing blob analysis again, just to locate the characters. And then we could crop these characters and train a neural network to be able to read these characters. So what you see here, we have MI278, and the context is reading MI278. But for I, for example, the score, which means how confident is the context for its prediction, is a bit lower than others. It's 88%, and the reason is because I and 1 are very close, so it's not sure that it's looking at I or 1. Segmentation is another way of using deep learning. So here, what you are looking at is a sheet of steel. There could be defects like pit defect or scratches on top of the sheet. So you want to look at this sheet and say if there is a defect or not. Here we are having a pit defect, and you see that there is an outline around that shows here there are basically defects, and the type is pit. Yeah, so the other example would be bin picking. Here we are using what we want to do, and actually what is bin picking? You have a bin full of products, and you have a robot that you want to take one product out of this bin and then place it into the right location. For this purpose, we need a 3D camera. So we actually scan all the surface of the bin. And then we can also use the camera to capture a model of the 3D the object and have a 3D model of the object. And then once we define the model, you can use our 3D matcher to match it with the best candidate that we have. For example, in the video that you're looking at, the part on top is the best is because it's closest to the camera, and the robot could be easily grab this. So I guess that's it for the, yeah, there was a miss, yeah. So,
right, whoops, my bad, I forgot. Right, my bit, right?
Yes, exactly.
Yeah. So we've seen some examples now of how you can use like classical vision and 3D analysis, and how you can use deep learning, and how we kind of like combine them together to actually be able to solve a lot of customers' problems. I think some of the caveats that people think about when they think about machine vision today is that they think about purely deep learning models, about using exclusively deep learning to solve vision problems. And the reality is, due to like the high accuracy and performance requirements of customers, that's actually really tough to do with just deep learning models. And that there's this whole branch of classical machine vision that's been around, since the 80s, that has actually improved a lot over the years, that we can leverage to actually solve a lot of these problems. And you saw that with like the muscles. We use blob analysis to help localize features we want to do some sort of deep learning with. And so I guess what we're driving at is that we're really at the intersection of classic machine vision and deep learning, and taking all that knowledge we have and all that industry expertise of doing like classical machine vision and combining it together to be able to do other things. So how do we actually do that and meet high accuracy and performance requirements? Well, I think it's important to remember that vision's only one part of the process, right? So you have like an assembly line somewhere and you want to find a part. But once you find that part, you need to control a robot, right? Robot has to come in and move that part in some way. And then ultimately you have to assemble things, right? Those parts are going to come together to make something. And the reality is that the find part, that's the vision bit. Afterwards, you've got to control robots, assemble things. All that takes a lot longer to do than finding the part, right? Finding the part, that's the algorithmic bit that we can really squeeze for time. So customers are really aware of that. Every moment we can save on the vision, where we can find a part a few milliseconds or a few microseconds faster, there's a few milliseconds more time the robot has to do something, which means more parts processed, which means more things assembled, right? It's just a numbers game. So performance is a real design constraint when we actually make our library. So on the left here, we're doing barcode reading. And so barcode reading is really popular. Lots of products have barcodes on it. And in this example on the left, it's a non-optimized standard run of barcode reading. And you can see from the little time in the upper left corner, it takes something like 12 milliseconds to read it, 13 milliseconds, 15 milliseconds. And you might say, that's pretty good. If you're a user with a cell phone looking at a barcode, well, what's 12 milliseconds? But in an assembly context where vision's only part of it and you've got robots and things that have to come in, that's actually like a really long time. So what we do is we actually have a whole optimization system where we optimize our algorithms and do the best we can to actually do the computations in a faster time. And the example on the left is the exact same example. The only difference is that we have our optimizations running. And now we can get things down to 2 milliseconds, 3 milliseconds. And even that, I would say, for some mill operations is very long. We have modules that run in the microsecond range. And these are running on general purpose computers, like ones you find at home, or even older equipment, right? Because customers buy hardware, like from 10 years ago, and they're still using it because it still works, right? So a lot of effort goes into making our algorithms work and trying to make them both accurate and performant. So how do we actually do that? If I can hit next slide. Right, so an average time of 15 milliseconds versus 2 milliseconds when we go ahead and optimize. Also remember that our operations involve complex arithmetic, right? You want to do something like find closed edges in an image. That's a really common thing. You want to find all these things that are closed, right? Well, how do we do that? We do that with differential operators, right? We have to do some derivative math on this image, which is the same in deep learning, right? Because gradient descent, right, everyone? So differential operators, you can't escape from them when you're trying to do something productive. And then at the end, we can find all the closed edges, and we can say, these rings are okay, and that ring is broken. But it took all these big differential operators. So the other constraint is that, in the real world, in these assembly lines, in these biomedical devices, right, deep learning is often performed locally, right? Customers have these industrial computers, like this is one of ours, Foresight, that are bolted to a factory wall somewhere, and they have fixed processing power. They don't have GPUs in them. They're typically CPU only. They're fanless designs, right? They have no moving parts. And these things will stay in service for a long time, like 10 plus years long. So the cloud is not really available to us. When you're doing development, people have access to the internet. But I think in runtime, when people actually deploy these things to factories, a lot of these computers are networked, but not necessarily to the internet. So cloud computing is really not available. So creating an industrial algorithm is key for us. A lot of work goes into research and prototyping as a starting point to try and figure out, how do we actually solve this problem? Can we make a module or an algorithm that finds what we want to find, can read the barcode, for example? But then a lot of work goes into implementing efficient strategies to try and figure out what the best way is to speed up these algorithms and where to make good trade-offs in terms of speed versus performance and accuracy and that sort of thing. So for us, optimizations are essential for high performance. And so a lot of our library, actually all of our libraries, coded in C, C++. You know, I know deep learning is very popular in Python, and people do a lot of prototyping in Python, and that's great for prototyping. But when it comes to actual industrial grade code, we actually do our implementations in C++. All of our algorithms use multi-core when possible. So they're using multiprocessing, multi-core in an attempt to speed up and parallelize as much of the work as it can, so it can be more efficient, so it can be fast. And how do we do that? Well, we do a lot of optimization work too. We leverage things like special CPU instructions like AVX and SSE and all these different chip features that your CPU has that usually are used for multimedia. We leverage a lot of that to optimize these algorithms and really make things performant, as I showed you before. And so that leads to this concept of intrinsics that you'll probably never hear about in school, but you'll hear here, and hopefully you'll think it's interesting. So intrinsics allow for this tailored behavior. So they're what we call compiler built-in. So that's why we like to be in C++, right, in C. And what they do is they map to special CPU features. So they expose special functionality of the chips that let us do all these multimedia instructions like SSE, MMX, etc. And what they do is they basically provide assembly-like functionality, but in C++ for us, where we don't have to write assembler code. Because I'm sure all of you had to do that for a course at one point. I never want to do that again. Well, neither do we. And so we use intrinsics for that. So what's cool about intrinsics is that they're portable and maintainable, unlike assembly code. So you have a code snippet like this. You want to do a multiply and add. Super common operation in most differential stuff. It's a multiply accumulate, you know, and you have these float arrays, and they contain 8 floats in the array. So you have an array of 8 floats, and you want to multiply them all and then add them together and then put that in a result. Well, you could do that naively like this in C++ with a for loop, with a multiply instruction and add instruction. But at the very least, this is going to take 8 for loop iterations to do, right? Because you at the very least have the for loop and 2 operations. So this can actually be quite long. But there are these cool instructions from intrinsics called MMM256. And this exact function, which is a C++ function you can call, takes an array of 8 floating point numbers and multiply and accumulates it with another array of 8 floating points. And so this thing contains 8 floats, just like our C code on the left, but it maps to 3 AVX instructions. So you save a bunch of CPU cycles just by calling this function, because you can do it in at least 3 cycles compared to the 8 or more cycles we have on the left. And so this is what industrial code looks like, to give you an idea of the difference between like the stuff you see at school and what we actually do with a lot of this stuff. And the cool thing about this is that these intrinsics support multiple operating systems and CPUs, so we can do it for like a whole bunch of different customers, which is really cool. So to briefly recap on what we saw, you know, what's machine vision? It helps us automate inspection. It doesn't just have to be deep learning. It can be all these other classical techniques too, and we can marry them together and make something cool. You know, deep learning can really solve a lot of interesting problems where, you know, classic machine vision gets stuck. You know, we can only go so far, so we can find the muscle, but we can't tell you if it's good or bad. Well, that's a great marriage of classic machine vision and deep learning. You know, operations are complicated and often involve differential operators and all these deep things. We have to think about, well, what does that mean for our application? What does that mean for the real world runtime of these things when we actually put them together? And then we talked a bit about intrinsics and how that actually allows us to make industrial code and put things together and make it actually potent and powerful for customers at the end of the day. And so that's it for us in terms of presentation. Does anyone have any questions? And organizers, feel free to point me at a resource if I'm supposed to be looking at a chat or something where questions appear, so I just see it.
Yeah, we're monitoring the chat right now. We'll if there's any questions. And if anyone has like extra questions, you could always ask Matrox in their channel in the Discord after.
Yep. So I believe someone is still sitting in the Discord. So if you have questions about the challenges, you can see that. Benham can correct me if I'm wrong, but we do provide you with an installation of Mill, which comes with Copilot, which is that UI you saw, where you can label images and do training. And we do our best to provide kind of easy tools for our customers who want to put them all together. So feel free to leverage that to solve any vision problem that you're trying to do. I mean, clearly ours is for vision. So if you're trying to do, I don't know, like natural language processing or something, you're out of luck. But if you want to label images and then train a model and classify, we do that, no problem. Any questions at all about, in fact, anything related to this, about the challenge, about what we presented, about industry and Matrox in general? We're happy to talk about these things.